Okay, let's dive into this. Welcome to This Explainer. Today, we're going to treat geotechnical engineering like the ultimate detective story. Because before we can build towering skyscrapers, sprawling highways, or even just a simple home, we actually have to decode the dirt right beneath our feet. We're looking at what engineers call index properties and classification tests. It's basically all about interrogating the Earth to see if it can actually hold up our ambitions.
Here's our methodology for the explainer. We'll cover 1. The ground beneath us. 2. Vital clues through index properties. 3. Hands-on field identification. 4. Shrinkage and consistency limits. And finally, 5. The engineering classification system.
So, starting with Section 1, the ground beneath us, why soil classification matters. This is absolutely crucial because the stability of literally every foundation depends entirely on the variable, complex materials they sit on.
And this brilliantly illustrates how natural soils are rarely pure sand, pure silt, or pure clay. They're intricate mixtures. You'll hear terms like sandy clay or loam, which represents a beautifully balanced mix of sand, silt, and clay. The soil texture triangle is our first real tool to visualize how these natural components blend together in the real world.
Moving to Section 2, Vital Clues, Index Properties. These are the specific, quick tests that help us determine the future behavior of a soil mass.
Before we even pull out the heavy lab equipment, we can get massive clues just by looking at the soil's color. Dark colors? Well, that almost always indicates organic matter, which definitely affects stability. If you see green and blue hues, that's often imparted by specific compounds like pyrite. And if you've got a stark gray or white soil, it usually means an absence of colored compounds, pointing us directly towards minerals like quartz or kaolinite. It's honestly amazing how a simple visual check reveals the hidden chemical and organic makeup of the ground.
Now let's zoom way in. These microscopic particle shapes might look like abstract art, but their literal, physical shapes dictate exactly how the soil will mechanically behave under pressure. Whether a particle is bulky, flaky, or angular directly determines how tightly the grains can lock together when we try to compact them to hold weight. It's kind of like a giant puzzle.
And speaking of compacting, that brings us to the density index, or ID. Simply put, this is a measure indicating the relative compactness of a coarse-grained soil. Instead of getting bogged down in heavy algebra, just think of it as a sliding scale. It tells us how tightly packed the soil currently is in the ground compared to its absolute maximum possible packed state.
Let's look at the extremes to really grasp this. On one end, we have the loosest possible state. This gives us a density index of exactly 0, meaning the void ratio, which is just the amount of empty space between particles, is at its absolute maximum. On the other extreme, we have the densest state, giving us an index of 1. Here, the empty space is minimized. So if your soil is closer to 0, it's loose and potentially very dangerous to build heavy structures on. If it's closer to 1, it's dense, packed, and stable.
All right, Section 3, Hands-on field identification. Sometimes we just don't have a pristine lab at our disposal, so we have to conduct our interrogation right out there in the mud.
So I want you to imagine you're standing in a trench on a muddy construction site. How do you tell silt from clay with just your bare hands? I mean, it sounds kind of impossible, right? But engineers actually have a specific set of tactile tests to figure this out on the fly.
Here's the bare hands interrogation protocol. First up, the strength test. If you dry a little lump and it breaks easily in your fingers, it's silt. If it requires real effort to snap, you've got clay. Second is the rolling test. Try rolling some moist soil into a tiny 3mm thread. Silt is just going to crumble apart, but clay is tough. You can roll it into a thread 30 centimeters long, and it will literally hold its own weight. Third, the dispersion test. Drop a spoonful in water. Silt settles in about 15 minutes, but clay particles are so microscopic they stay suspended in a cloudy mix for hours. And finally, the shine test. Cut the wet soil with a pocket knife. Clay leaves this shiny, soapy surface, while silt remains completely dull. Just imagine that soapy, sticky feel versus a crumbly, dusty texture. Your bare hands are basically the lab equipment.
Which brings us to Section 4, Shrinkage and Consistency Limits. Adding moisture totally transforms fine-grained soils, sometimes turning a rock-hard block into flowing soup.
To measure this vulnerability, we use the Consistency Index, or IC. This is the ratio of the difference between the soil's liquid limit and its natural water content to its plasticity index. So the crucial point here is this index tells us exactly how the soil behaves right now in its natural, undisturbed state in the ground based solely on how much moisture it currently holds.
And here's the final verdict. If your consistency index is greater than 1, the soil is in a semi-solid state. It's stiff, which is generally great news for building. But if the consistency index is less than 0, the natural water content actually exceeds the liquid limit. That means the soil behaves like a liquid. Think about the so what factor here. If you're an engineer and your index is less than 0, you're essentially attempting to build a structure on a liquid. That is a massive, catastrophic red flag.
Finally, Section 5, the Engineering Classification System. This is where all of our clues culminate into one universally understood language.
So here's your classification cheat sheet. We assign a single letter to each primary soil type to keep things standardized globally. G is for gravel, S for sand, C for clay, O for organic, and peat for peat. But notice silt. Silt is designated with the letter M. Why not S? Well, because S was already taken by sand. So M actually comes from the Swedish word mo for silt. It's a fantastic little piece of international engineering history hidden right there in the codes.
Next, we take those primary letters and add modifiers or subdivisions to give a complete picture. W stands for well-graded, meaning a really good mix of all particle sizes, which is usually great for compaction. P is poorly graded, meaning it's mostly all one uniform size. Then we have modifiers for how the fine-grained soil handles moisture. L for low plasticity, where the liquid limit is under 50%, and H for high plasticity, where it's over 50%, meaning it's highly compressible.
Finally, we combine the clues to name our culprit, so to speak. If you see the symbol GW on an engineering report, you instantly know you're dealing with a well-graded gravel. If you see CH, you know for a fact you're looking at a high-plasticity clay, a soil that's going to swell and shrink dramatically with moisture changes. Just two simple letters, but they contain absolutely all the detective work we just covered today.
We've decoded the dirt, from microscopic particle shapes to bare-hand field tests, translating it all into a global engineering code. So I'll leave you with this. Next time you walk outside, what hidden mixture is supporting your every step? Is it a stable, well-graded gravel, or a high-plasticity clay just waiting for a rainstorm to turn liquid? Thank you so much for joining me on this explainer, and keep questioning the ground beneath your feet.